Hey guys, what's going on? So today we're going to be talking about a very important realization of a type of basis that we're going to use throughout the rest of this tensor calculus series. And so without further ado, make sure to hit that like and subscribe button. You can also go into my Patreon page where you will find exclusive content as well as early content. So when I start these playlists again, I'm not putting exclusive or early content on these. I want them to be totally free, totally available to you guys. And then as the playlist progresses, anything that's a little bit more time consuming for me to make, I'll put on Patreon. With that being said, let's get right into the topic. So today we are going to be going over an important realization for a basis. So up until this point, we've been using this sort of obscure E mu and E nu as basis vectors for our vector spaces. The question becomes, is there a sort of physical or mathematical tangible object that behaves like these vector spaces? Excuse me. So we can consider a function on spacetime, right? So this is somewhat abstract, a little bit obscure, but conceivably we can think of, say, a temperature field, or a function of temperature in space-time, right? So I'm sitting here at this point in space. There is a certain temperature, okay? We can also think of maybe a potential field, okay? We can think of maybe the strength of an electric field at some point in space and time. So these are all functions on space-time. There's some value that we ascribe to a point in space and at a moment in time, right? So these are functions on space-time, and they're functions of four independent variables: x0, x1, 2, and 3. And each one of these corresponds to time, the x direction, the y direction, and the z direction. So if we have a function on space-time, we can take derivatives of that function as well, right? So here are those derivatives. We could take a derivative as with respect to time, or we could take derivatives with respect to any spatial dimension. So using this prescription now, we have this idea of a function on spacetime. We're able to establish a unique vector space at each point in spacetime that solely depends on that function, okay? And having this vector space is this partial operator, d mu, as a basis. And we're going to call this a coordinate basis, okay? And here's how this goes. So we have d mu acting on f. This is an operator. When we operate on the function, right, that's going to give us expressions for all of these, okay? We also have our vector, right? So our vector is a mu, and that can change at various positions in space or at various moments in time also. And so when we flesh this all out, we have derivatives as a function of spacetime, right? So that's this covector, okay, right here. We call this a covector, right, because it's a lower index. We call this a contravariant, or just a vector, because it has this upper index. And so we write this as a vector, okay? So this guy here, this is going to be some expression, some x plus y, say, okay? That's going to be this right here. Then these are all going to be values or some sort of expression as a function of x, y, or z or t. And then at that point in space-time, at point P, right, so that's going to be, say, at this point, we evaluate all of this at point P, right? And when we do that, that collapses us to a number, okay? So with fleshed out a little bit more, so these 0, 1, 2, and 3s, we always want to sort of refamiliarize ourselves with what the 0, 1, 2, and 3 actually mean. This is time x, y, and z, time x, y, and z. and then all of these guys here run over each independent variable as well. Okay, and then we can evaluate all of this at p, and that brings us to a number. So by evaluating at p, this object becomes a number. All right, so that means this object right here is a vector in our vector space, right? Because this was a covector and this is a vector. So this is a legitimate object in our vector space at every point in our space-time. Okay? So up until this point, we've been talking about vector spaces at each point in space. We now want to put a name to these spaces, and we are going to call them tangent spaces. So here's what we're doing. So this is a tangent space because these are derivatives. These are derivatives of a function, and derivatives of a function are the tangent vector to that function. That the tangent tells us what the derivative is at a particular point, say p again. So when we rename these, we call this TP, so tangent space at P, and TP stars is cotangent space at P. Right, so this is a cotangent space. This is a tangent space, 2f at spacetime point P, 2f at spacetime point P. Right, these can be tangent metric spaces as well. So we put a metric in here. But when we put a metric in here, we can also create that rank 0 to tensor that mimics this metric. And we'll talk about that in a few minutes. So suppose now there's a coordinate transformation, because what we want to do now is we want to see what happens if there's a transformation that occurs in the basis. How exactly do these basis vectors change? So if we suppose now that there's a coordinate transformation, we go from a coordinate transformation that looks like this to maybe something that looks like this. This might be a black hole sort of. This looks like there might be a black hole right here. Right? I'm just sort of drawing two different coordinate bases, and I want them to look different, right? Because this is a coordinate transformation, and so what we do here is we say, well, x mu is a function of x mu, or is a function of x mu prime, right? So x mu prime is the new coordinate basis. Similarly, x mu prime is a function of x mu. So that means if we take a function on x mu, well, that function is a function on x mu, which is a function of x mu prime. We're really just putting both of these inside a function. We're taking the function of both sides, almost, if you will. Okay. And so we have these two expressions, okay? And we could say, well, what is the derivative of the function with respect to the new coordinate basis? Well, just by chain rule, we take the derivative of the function, okay, and then we take the derivative of the coordinate basis, and we take the derivative of that coordinate basis. We see here that this is where that new coordinate basis helps, right? So, and these two guys are conceivably cancel out with each other. So to write this out a little bit more, it's going to be df dx mu dx mu dx mu prime, right? So those guys, and we get the derivative of the function with respect to the new coordinate basis. Okay. And so what is this? So this guy right here we're going to call this a matrix, right? And this matrix looks like, we're going to say nu on the bottom, mu prime on the bottom, which is that new coordinate basis, and mu on the top, which is the old. So our expression now looks like this, and we can now take out the function on both sides, because this is just the operators are really what we're looking at, And when we do that, we are seeing here that this is the expression, right? So these matrices, this is a Jacobian matrix. If you haven't seen Jacobian matrix before, this is what it looks like. Right? So news on the bottom, right? So we have 0, or the temporal dimension, right? X, Y, and Z. And then we have temporal X, Y, and Z on the top. Okay, so this Jacobian matrix looks like this, and the inverse is going to look like this. Okay, and we're going to see why this is the inverse of this, right? You can kind of just look at it and see, well, the new coordinate base is on the bottom here, new is on the top here, so they must cancel out to some, they must have some cancellation properties to them, and we'll see why in just a few seconds here. But let's go over a summary really quick. So our summary, in the past 2 or so videos, we've talked about contravariant transformations, which look like this, covariant transformations, which look like this, and then tensor transformations, which look like this. Okay, the point being that, let's actually do this, right? So I'm going to erase all the indices now, because the point I really just want to make here is that like this, and then I will bring these guys closer together, is that we just really want to see how these things transform. Okay, and then I'll bring this guy close. So the covariant objects are going to transform inversely, in an inverse way, when compared to the contravariant objects. Tensors transform in a unique way, right? This is just one example. And so now we have these guys, right? So these are the transformation bases for the transformations for the coordinate basis, right? So these are the coordinate bases, and we're going to see now. We're going to see now how these two guys right here, this one and this one, are inverses of each other. And what we want to show is that this is what it means to be an inverse again, or not inverse. This is the condition we want. We want the covariant object and the contravariant object to be to look like this, right? This is the Kronecker delta. So let's go ahead and calculate this. So this guy right here is this guy right here, right? We just transform. These are new basis coordinate. These are new coordinate bases, which are transformed old coordinate bases, so that those look like these. Okay. And then, so we can bring out the matrices in the respective order, right? And then we have this right here. This right here we've already established was this, and so we can bring the news equal to the mu's, and when we do that, we see mu and nu. So this is the guy we're changing right here, because we're changing mu into nu, or nu into mu, and that's that change right here. These two guys, Einstein, sum over each other, and all we get left is this, right? So that's this guy right here. This means that the tensor transformation of mu, or del mu and dx mu, are actually inverses of each other. So we've now proven that this indeed, or by using this, we've proven that these two guys right here are indeed inverses of each other. Okay, let's take a look at what this looks like in terms of a tensor. And we're going to pick the metric tensor. So here's a metric tensor in an old basis. Okay, so LK, DLK, DXK. So here's our GLK, and now we're going to transform the basis. This is in some new basis, right? So these guys we've shown transform in this way, right? And then these guys are going to transform in this way. right? Because here is that transformation, and actually we are doing this as no, this is, I think this is fine. So this is that new basis, and what we have here is, so the point here is that we want these guys to sum over each other, right? These guys are summing over each other, and then the L's and the K's are summing over the components, okay? And so what we get is this right here. So this is that new basis, and here's that transformation. Okay, so when we look at the coordinate transformation for just the components of the metric tensor, we get these equations right here, right? And so the point here is that we really just want to sum over. Again, these were the these here were the Jacobian matrices, right? So that's these guys. When we flesh them all out, this is what they look like. And we have G, I, J, and LK. LK are summing over indices, and we have these right here, okay? And last but not least, we have similarly how the rank 2-0 matrix transforms as well. The rank 2-0 metric tensor transforms in this way. Okay. So that's what we have, right? So this is this means also that when there is a change in the basis of the inner product, right? Because these guys mimic, these are the values that we get for the inner product in each individual vector space. That since they change in this way, then that means the inner product, the values of the inner product, will also change under a coordinate basis. And by means of how so we can calculate the metric, right? By means of the metric, calculate the metric, and so once we do that, we can calculate what the inner product, what we know what the inner product is under this transformation basis. But anyways, again, if you like this kind of content, make sure to hit that like and subscribe button. Make sure to go on my Patreon page, again, where you can find exclusive and new content. And with that being said, I will see you guys in the next video.